University. And I'm here to talk about some of the research that I did with Dr. James Bisgard. So the presentation is entitled Investigating Qualitative Properties of the Third Smallest Eigenvalue of the Graph Laplacian. There's a lot of words there, so I'm going to talk about what some of that means and then get into the fun stuff. So this is looking into a field of math known as spectral graph theory. And spectral graph theory is sort of a subfield of traditional graph theory. However, it's done through the lens of linear algebra and specifically the eigenvalues and eigenvectors of matrices that embed a given graph. So there's just a little example of it. Definitions is a big one is going to be the graph Laplacian. This is a very common way to embed a graph. A common one that you may see is the adjacency matrix. However, we focused entirely on the graph Laplacian. And that is just a matrix L with entries Lij defined as -1 if vertex i is connected to vertex j. We have the degrees of the vertices along the main diagonal and then 0 otherwise. The reason we call it the graph Laplacian is that it has some nice analogs to the Laplacian operator from real analysis and differential equations and all that. There are places where that sort of falls apart, but it's close enough that it was given that name. And then, as we're talking about spectral graph theory, we should have a spectrum. And this is just the sorted list of eigenvalues of whatever graph we're talking, or whatever matrix we're talking about. However, as I'm talking about just the graph Laplacian, if you hear me say the spectrum of a graph, know that I'm talking about the spectrum of the graph Laplacian of a graph. There's spectral graph theory is relatively new, and so the notation is kind of all over the place right now. So we express the spectrum as sigma of g is equal to lambda 1 all the way to lambda n, and these are sorted from least to greatest. You will see some sorted from greatest to least. But for this, we will be talking about least to greatest. Some main ideas is that we should cover is that there's some properties of the eigenvalues. Notably, they are real and non-negative, as the Laplacian matrix is positive semi-definite. This makes things pretty nice to work with. And furthermore, if you're working with a simple graph, your eigenvalues are bounded by n from above, where n is the number of vertices. We've also got what is known as the algebraic connectivity. This is a pretty big concept in spectral graph theory. This is a value that describes sort of how well connected a graph is. It can be thought of in a few ways of sort of like heat transfer or heat dissipation. So if you have a graph and you heat up one vertex, how well that heat will dissipate through the system can be expressed by your algebraic connectivity. So a graph with a relatively large algebraic connectivity will dissipate heat very well, and inversely, a very small algebraic connectivity will dissipate heat very well. And kind of going hand in hand with this, we have the multiplicity of 0. So the spectrum allows for repeated eigenvalues. It's not necessarily a set, that's why we call it a collection of eigenvalues. And furthermore, the amount of times that 0 shows up in your spectrum is the number of components in your graph. And so kind of going with that, you can think of as the algebraic connectivity gets closer and closer to 0, the closer you are to having multiple components. That's kind of maybe an intuitive way to think about it. So what were we looking at? The big question kind of driving this research was, we know what lambda 2 represents, the second smallest eigenvalue. We know what that represents, being the algebraic connectivity. What about lambda 3? And does it even represent anything? That's kind of a big question to ask. So narrowing down a little bit, we ask what properties do certain graphs have that might correspond with their eigenvalues. With the third smallest eigenvalue. And furthermore, is there any conjectures and generalizations that we can make along the way? So we approach this problem by first looking to maximize or minimize eigenvalues on given graphs, and just seeing what things pop out of there, just looking at these extreme cases. And so we would use a greedy algorithm for this, where we would just plug in a graph and delete an edge and replace it somewhere else and see, did lambda 3 increase? If yes, just keep repeating that until we hopefully find a nice maximum. Now it is a greedy algorithm, so it may not find the global maximum, but it does find some nice maximums. we were doing this mostly with what are known as Wagner graphs. These are 3 regular graphs on 8 vertices. And what we found is if we plugged in a Wagner graph, we would get this. We'd have the disjoint union of these 2 complete graphs on 4 vertices each. Now there's a few things that you could notice here, but one thing that I noticed after staring at it for far too long is that we have 2 areas of incredibly high connectivity. We have, in fact, perfect connectivity over here and perfect connectivity over here. However, they're completely disconnected from each other. And so kind of a thought there is that maybe lambda 3 has something to do with maybe localized connectivity in the graph. So that is a graph that has a relatively large lambda 3. It might have areas that are very well connected, regardless of how well connected the entire graph is. To be honest, I don't have that's pure conjecture. I don't have a full proof for that. That is it's kind of above me right now, but we're working on it. What we do have is a nice little result, which says that for a simple undirected and unweighted graph on n vertices, partitioning that graph, that is cutting it up into disconnected components, partitioning that graph and looking at the algebraic connectivities of those individual subgraphs, those will be bounded by above from the 3rd eigenvalue of your parent graph. And in English, that's just saying that there does not exist a partition of a simple undirected and unweighted graph G such that the resulting subgraphs each have algebraic connectivity greater than lambda 3. So to actually show this guy, we need a lemma just to get us started. And this lemma is saying that for a finite undirected simple unweighted graph on n vertices, we're going to let G prime just be G with the removal of an edge. Then we can show that the kth eigenvalue of G prime is always less than or equal to G. And similarly the other way around, if we add in an edge, then lambda k of G will be less than or equal to lambda k of G prime. Just saying that removing an edge cannot increase your eigenvalues, adding an edge cannot decrease your eigenvalues. I'm not going to go through and show the whole proof. I'd be happy to if anyone wants to see it, but for the presentation, not going to do that. But you can show it using the min-max theorem. That is the min-max theorem, not the minimax theorem, formed by Courant-Fisher. And you can do this expressing edge addition and removal as the sum of your Laplacian matrix and the outer product of 2 vectors, so that L plus BB transpose is equal to the Laplacian of your new graph. Now, using that, we get this proof in that showing that previous theorem that we had, we're going to let G be a simple, undirected, unweighted simple graph on n vertices, and it's going to have the spectrum sigma of G of lambda 1 of G all the way up to lambda n of G. Now we're going to partition G in such a way that we get 2 disjoint components, where G1 and G2 are subgraphs of G. And we're going to call this post-partition version of G, G prime. Well, as the multiplicity of 0 in our spectrum is the number of components in our graph, we know that G prime is going to have the spectrum 0, 0, lambda 3 of G prime, all the way up to lambda n of G prime. And note here that as this is a sorted list, lambda 3 of G prime is actually going to be the minimum of your algebraic connectivities of those 2 individual subgraphs. But from our previous lemma, we know that G prime is just G with the removal of edges. That's what a partition does. So we know that lambda 3 of G bounds from above lambda 3 of G prime. But also, lambda 3 of G prime is just the minimum of these 2 algebraic connectivities. So that means that lambda 3 of G prime is always greater than or equal to the minimum of lambda 2 of G1 and lambda 2 of G2. So that means that the 3rd smallest eigenvalue of G provides an upper bound for the lesser of the algebraic connectivities of the 2 subgraphs induced by partitioning G. And once again, just in English, that is saying, where did that go? That there does not exist a partition of G, so that you can cut it up and have both subgraphs have greater connectivity than your first 3rd smallest eigenvalue. So that's about as far as we've gotten with the sort of big questions answered. But taking it further, There were a few cases where lambda 3 of G was actually greater than both of these algebraic connectivities. It happens kind of often enough that it begs the question of when does this happen? When can we force this? And is there a partition we can do that could force this relation or maybe other relations? And furthermore, what generalizations can we make? I'm sure this isn't everything. So, what other questions are there to be asked? What other questions are there to be answered? And then mostly just for me, what fields could I look into to improve my intuition and my understanding of all of this? Actually, I have an answer for that, but if other people recommend things, that would be great. And just some final conjectures and ideas is that partitioning with respect to the eigenvector corresponding to your third smallest eigenvalue, actually, it looks like it gives that relation where lambda 3 bounds the maximum of these two algebraic connectivities. Fully honest, I haven't looked at a ton of cases of this. However, with the ones that I have, it looks to be this way. And kind of the big conjecture that this whole research is that lambda 3 provides some information about maybe how partitionable a graph is, or maybe the localized connectivity of a graph. Again, just conjecture, I haven't shown that. And I'm thinking of looking into hypergraph theory and further into analysis, just to get some better understanding of the generalizations of graph structures and some better understanding of the Laplacian operator and boundary value problems, all that fun stuff. So thank you all for listening. That's it.
So you had mentioned a little bit earlier about looking into other fields that this potentially might be connected to.
Yeah.
Aside from just the lambda 3, what do you know of any fields that it's more appropriate to use, like the Laplacian matrix versus other types of matrices?
I don't know a ton off the top of my head. I know that there are actually different forms of the Laplacian matrix. One you'll commonly see is the normalized form, where all the values are between 0 and 1. I know graph theory sort of as a whole is very common. Things like civil engineering with like road maps and networks and that kind of stuff. So no, I don't really know a whole lot of other fields where this gets used a whole bunch. I know that actually I do know that physics, people are trying to use hypergraph theory and some spectral things, I assume, to look for a general model of the universe. I'm trying to tie all these things together. So
would it be safe to say that maybe Laplacian graphs are better suited for maybe more like rigid rather than like fluid concepts like social networks?
I would say so, being like a form of discrete math. Yeah, but I'm sure however many ways you want to look at it, you can pull as much information out of it as you want. So yeah. Other questions?
Can you tell us a little bit about how you got interested in this topic?
Oh yeah, Dr. Bisgar hosted a honors seminar in spectral graph theory. I don't know, just kind of scratched an itch in my brain. I found it pretty interesting. And he was the one first asked the question of what does lambda 3 represent? And so we just sort of kept looking at it from there. And yeah, just stuck with it. I think I can do it.